Hi, we're going to talk about Taylor MacLaurin series. So in the last section we spoke about different functions that could be represented as series. For instance, if we have the function 1 over 1 minus x, this will be equal to 1 plus x squared, etc., as long as the absolute value of x is less than 1. Right, and this could also be written as the sum from n equals 0 to infinity of x to the n. So that's one function that can be represented as a power series, but a much broader class of functions can be represented as power series. So we'll start with supposing that f of x can be represented as a power series. So c sub n x minus a to the n, where n goes from 0 to infinity. Now let's consider this function. Let's just think about it abstractly. What's the value of this function at a? Well, at x equals a, we have c sub 0 plus c sub 1 times a minus a plus c sub 2 times a minus a squared, etc. Plainly, every term after c0 vanishes, so this is just c0. Okay? What happens when we take a derivative and then evaluate at a? So, taking the first derivative, we have c sub 1 times, so the x minus a drops out, plus 2 times c sub 2 times x minus a, plus 3 times c sub 3 x minus a squared, etc. And we're evaluating this at x equals a. Okay, so clearly everything that has a factor of x minus a vanishes, so we're left with c sub 1. Okay. If we do the same math for the second derivative, which we sometimes write with two apostrophes, sometimes we write it like this, with a parenthesis and a 2 sitting above f. This will be equal to 2c sub 2 plus 3 times 2 c sub 3 x minus a plus 4 times 3 c sub 4 x minus a squared, etc., all evaluated at x equals a. And plugging in a, everything vanishes after the first term, which is 2c2. Okay, so you probably see a pattern emerging. Every coefficient of this power series is related to the derivatives. And we can, if we did this a few times, we would see a formula developing that the nth derivative of f evaluated at a is going to be equal to n factorial times c sub n. Okay. Equivalently, you could write this as c sub n equals the nth derivative at a divided by n factorial. Okay? And I should observe that this is all taking place where x minus a is within some radius of convergence. Okay. So we can use that identity to give us a recipe for computing a power series expression for a function. So Okay, in particular, we can write f of x is equal to the sum from n equals 0 to infinity of the nth derivative at a divided by n factorial times x minus a to the n. And we should note here that this is true only for x within some radius of convergence, and also by convention the 0th derivative of a function at a is just equal to the value of the function at a. Okay. So this is called the Taylor series. For f of x at a. Okay? And because the choice of a equals 0 is special, when a equals 0, it is called the Maclaurin series. Okay? So let's do an example. Let's try to figure out what this Taylor series looks like for a familiar function. So let's do this example. Find the Maclaurin series for f of x equals cosine of x. Okay? So, because we're looking at a Maclaurin series, that's the Taylor series at a equals 0, so we're going to need, so f of x will be equal to the sum from n equals 0 to infinity of the nth derivative at 0 divided by n factorial times x to the n. Okay? So let's start by figuring out what the derivatives of cosine are. So let's say n, and this will be fn of x. So for 0 we have cosine, because that's just the function. For 1, it's the first derivative, or minus sine. 2, we have minus cosine, second derivative. At 3, we get back to sine. And at 4, we're back to cosine. Okay, so plainly after you get to 4, you're back at cosine, so you'll just continue taking derivatives as normal. You'll continue cycling through those derivatives. So now let's see what the values of these are at 0. So we get cosine of 0 is equal to 1, sine of 0 is equal to 0, which means minus cosine is minus 1, sine is still 0, and cosine is 1. Okay. So plugging that into this expression, we have f of x equals, well, the 0th term is just 1. Okay, then adding in the 1th term is 0, so we'll ignore it. The second term is negative 1 divided by 2 factorial times x squared. Okay, we'll skip the third term as well. Fourth term, positive 1 divided by 4 factorial times x to the 4th. Okay, and this continues. Okay, so if we wanted to write a general term for this, so we have, just to write this down again, we have f of x equals 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the fourth. If we had kept going, we would have gotten minus 1 over 6 factorial x to the sixth, etc. A general form for this is sum from n equals 0 to infinity of minus 1 to the n, okay, and that's what gives us the minus sign. In the denominator here, we always seem to have n factorial, 2n factorial. Okay, that's the even number factorial in the bottom here. And then we have x to the 2n up in the exponent. Okay? And one thing that's important to note here is that by convention, and for many very good reasons, 0 factorial is equal to 1. Okay? But what this tells us is that cosine of x is equal to minus 1 to the n, x to the 2n, divided by 2n factorial, where n equals 0 to infinity. This is the Maclaurin series for cosine. Okay. What's the radius of convergence of this series? Well, in general, when we're doing a radius of convergence computation for a power series, we will use either the root test or the ratio test. Since we have factorials in here, we should apply the ratio test. So we have absolute value of a sub n plus 1 divided by a sub n is given by absolute value of x to the 2n plus 2 divided by 2n plus 2 factorial divided by x to the 2n over 2n factorial, which is equal to x to the 2, just x squared. We should probably put an absolute value, but because it's a real number, we don't really need it, but let's put the absolute value in for now. Divided by 2n plus 1 times 2n plus 2. Okay. So the limit as n goes to infinity of that quantity this is always going to be 0 regardless of the x. Okay, so for any fixed x, this is going to be 0. So this means ratio test implies convergence for all x, which means r equals infinity. Okay, and the interval of convergence is minus infinity, positive infinity. Okay, so that's our Maclaurin series for cosine. So that's a Maclaurin series, but what will we do, how could we expand cosine if we're looking at a different x value, at a different central a value? So for instance, what if we're asked to find the Taylor series for f of x equals cosine x with a equals pi over 4. Okay. So our table of derivatives will look the same. Okay, with the same functions. It'll just be different once we plug in values. Okay, so 0, 1, 2, 3, and then it will cycle around. So we have cosine x as the 0th derivative, which is just the value of the function itself. Minus sine x is its derivative. Minus cosine x is the next derivative, and positive sine x is the next function, next derivative. Now let's consider the value at pi over 4. So pi over 4 is 45 degrees, so it's the right triangle with equal legs. So cosine is going to be 1 over the square root of 2. Sine is going to be the same, because both the adjacent and the opposite have the same length. So minus sine x is minus 1 over square root of 2. Minus cosine x is minus 1 over square root of 2. Sine x is 1 over square root of 2. Okay? So when we plug this into our formula for the Taylor series, we get is f of x equals, the 0th term will be 1 over the square root of 2, followed by the first term, the n equals 1 term, which will be, so it's the minus 1 over the square root of 2, that value, divided by 1 factorial times x minus pi over 4. Okay, now the n equals 2 term will be minus 1 over square root of 2 divided by 2 factorial times x minus pi over 4 squared. Okay, the next value will be 1 over the square root of 2 divided by 3 factorial x minus pi over 4 cubed. And so on, we'll do one more, plus 1 over square root of 2 divided by 4 factorial x minus pi over 4 to the 4th, etc. So how would I write a general term for this? Right? It's not quite alternating because we have positive, negative, negative, positive, positive, negative, negative, positive, positive, negative, negative, etc. So what I think we ought to do is split this up into 2 alternating series. Okay. So f of x will be equal to, we can actually factor out 1 over the square root of 2 from everything, because every term ends up having a factor like that. So for the first series, I want to take all of the even terms. That will be 1 alternating series. So it'll be n equals 0 to infinity of minus 1 to the n, since it's alternating, and then divide that by 2n factorial times x minus pi over 4 to the 2n. And then the other alternating series here is the odd terms, and that's given by sum from n equals 0 to infinity of minus 1 to the, let's call this n plus 1. So we'll want to put n plus 1 here because the first time you plug, so when you plug in n equals 0, it's negative. So that's why I want to put n plus 1. And down here will be 2n plus 1 factorial times x to the 2n plus 1. Okay? So it looks kind of complicated, but really it's just splitting it up into two series. One's alternating with even powers and even factorials, and one's alternating with, oh shoot, this should be pi over 4. And this one is alternating with odd factorials and odd powers. Okay, so let's look at another example. This one is a bit unusual because the function is not actually, it won't have an infinite series of terms in its Taylor series. It will have a finite number of terms because it's a polynomial. So let's take p of x equals x plus 1 raised to the 100th power. Okay? So obviously that would be a very large number if we are away from x equals minus 1 at all. So at x equals minus 1, this is going to be 0, plainly. And at x equals 0, it'll be 1. But if you go a little past x equals 0, so that you have a number greater than 1 there, you're raising it to 100th power, so it's going to get large fast. But let's try and compute the associated Maclaurin series. So here we're going to draw out the same chart as before. Let's call this p, the nth derivative of p of x, and then the nth derivative at 0. Okay, so we'll start with 0, 1, 2, 3. We'll see how far we want to go. So the value of the function at x is just x plus 1 to the 100th, and that's equal to 1 at x equals 0. The first derivative is 100 times x plus 1 to the 99. Right, just by chain rule, the derivative of the inside is 1, so you can just use the power rule. So this is 100. For number 2, it's going to be 100 times 99 times x plus 1 to the 98. So this is 100 times 99. And then for the third derivative, we have 100 times 99 times 98 times x plus 1 to the 97. So at x equals 0, this is equal to 100 times 99 times 98. Okay? Probably get the sense for where this is going. So when we want to expand this as a Maclaurin series, we'll have p of x equals 1 plus 100 divided by 1 factorial, which is 1, x, plus 100 times 99 over 2 factorial, x squared, plus 199/98 divided by 3 factorial, x cubed, etc. Okay? So we're able to compute the Maclaurin series even when it's not a function that has infinitely many derivatives. And if we wanted to find a general form, so what you might have noticed is that what we were basically dealing with is the product of 100 times 99 down to some 100 minus k, or 100 minus k plus 1 really, divided by k factorial. Okay? And this is sometimes called the binomial coefficient. It's written as 100 over 100 choose k is equal to 100 factorial divided by k factorial times 100 minus k factorial. And we read it as 100 choose k. Okay. These are also called binomial coefficients. So, what we found with the last Maclaurin series is that p of x is equal to the sum from n equals 0 to, let's actually just say to 100, because once you get higher than 100, you don't have any more terms, since this is a polynomial of degree 100. N equals 0 to 100 of 100 choose n times x to the n. Okay. And you can plug in the first few terms to see that this is true. When we have 100 choose 0, that's equal to yeah. Well, certainly in this formula, that's equal to 1. So we have 1 plus 100 choose 1 is 100. Uh, 100 choose 2, x squared. 100 choose 3, x cubed, etc. Okay, and that's exactly what we found earlier. All right. So that's polynomials. I think it would be useful to have kind of a dictionary of some standard Maclaurin series you should be familiar with. Okay. So the first one that we worked on in the last lesson was 1 over 1 minus x, and this is equal to x to the n, as you know. Okay. Next, e to the x. This is nice because every derivative of e to the x is also e to the x. So evaluating at 0, it's always 1. So the derivative term is always just 1, and we're left with x to the n divided by n factorial, where n goes from 0 to infinity. Okay? Oh, I should note that this is true for x less than, absolute value of x less than 1. This is true for all x. For sine x, we're going to have minus 1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial, taking this from 0 to infinity, and this is true for all x. Similarly, cosine x is going to be the sum from n equals 0 to infinity, minus 1 to the n, x to the 2n, divided by 2n factorial. This is for all x. So you'll notice that sine and cosine are very similar, which is kind of what you would hope for since they are each other's derivative, right? Also, you notice that sine, we often call it an odd function based on its symmetry. What that comes out in terms of the Taylor series is that it only has odd powers, whereas cosine is an even function and it only has even powers. That's an oversimplification of the relationship between those two ideas, but it's a good mnemonic. Okay. Those are a few. I'll just do a few more. So if we have arctangent of x, this is given as the sum from n equals 0 to infinity of x to the 2n plus 1, minus 1 to the n, x to the 2n plus 1 over 2n plus 1. And you can obtain this by taking the integral of 1 over 1 plus x squared, the power series associated to 1 over 1 plus x squared. So this is going to be true for all x with absolute value less than 1. And the next one I want to mention is ln of 1 plus x. This is given as the sum from n equals, let's start at 0, 1, n equals 1 to infinity of minus 1 to the n minus 1, x to the n over n. Okay. This is also true for absolute value of x less than 1, and this is what you'll get from integrating 1 over 1 plus x. And finally, a generalization of what we just did, 1 plus x to the k, so we used 1 plus x to the 100, but this is actually, a generalization is true for any k, that 1 plus x to the k is equal to n equals 0 to infinity of, we'll write k choose n, x to the n, where k choose n is called the generalized binomial coefficient, and it's written as k times k minus 1 down to k minus n plus 1 divided by n factorial. Okay, that's the generalized binomial coefficient. It works even if k is not an integer. K non-integer allowed. Okay, so I just gave you a few common Maclaurin series, and you might say, what does this do for me? Why do I want to have these Maclaurin series in my back pocket? And there are a lot of cool things that you can do knowing these Maclaurin series. You can generalize to other functions. So for instance, if I want to know the Maclaurin series for f of x equals 2 to the x. Okay, so one way I could approach this is using the definitions. I could take, well, the derivative is 2 to the x times ln 2, and then evaluate it and do that several times. Or I could re-express this as e to the x ln 2. Okay, it's another equivalent expression. And this, I can just plug this into the Maclaurin series for e to the x. So the Maclaurin series for e to the x is n equals 0 to infinity of x to the n over n factorial. So here it'll be x ln 2 to the n over n factorial, which means that I can simplify this by distributing the exponent and get n equals 0 to infinity of ln 2 to the n divided by n factorial x to the n. Okay, and that's the Maclaurin series for 2 to the x. Okay, another way that this is helpful is if you want to find a power series expression for an integral. So let's do the following problem. Integrate sine x over x dx using power series. Okay? So sine x over x doesn't have an elementary integral. But what we can do is, we'll note that sine x has this Maclaurin series expansion, n equals 0 to infinity of minus 1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial. So when I take sine x over x, all I have to do is subtract 1 from each x term. Okay, double check that that doesn't give you anything with a negative power, because then that will cause some trouble. But x to the 2n plus 1 is always at least x, even for n equals 0. So we can just make this x to the 2n. Then we have 2n plus 1 factorial. And if we want to integrate, we'll get integral of sine x over x dx. Well, we can integrate term by term, as we did in the last section. So we'll get the power series n equals 0 to infinity of the integral minus 1 to the n x to the 2n over 2n plus 1 factorial dx. And then we'll get a constant term out there as well. So this will be given by n equals 0 to infinity minus 1 to the n, x to the 2n plus 1 divided by 2n plus 1 times 2n plus 1 factorial, okay, plus c. Okay. So this helped us get a power series expression for an integral that we don't even know how to compute. Okay, so that's pretty nifty. We can also use power series to compute limits. We want to compute the following limit as n goes to infinity of apologies. This really should be limit as x goes to 0 of x cubed minus 3x plus 3 arctangent of x divided by x to the 5th. Okay. So the reason that it's useful to use power series is that anything with a factor of x is going to vanish when we send x to 0. So we want to look at this function and figure out what part of it is constant and the rest of it is powers of x. So we use power series to do this. So we know that arctangent of x, looking at our table from before, this is equal to the sum from n equals 0 to infinity minus 1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial. I'm sorry, no factorial. So this is given by, so when I multiply by 3, so we'll get so this is the power series expansion, and when I plug that into the expression, so when I take 3 arctangent of x and expand out the first few terms, I'll get, so the first term is x, next term is minus x cubed over 3 plus x to the 5th over 5, okay? And when we have 3, so we have to multiply everything by 3, okay, etc. So this is 3x minus x cubed plus 3/5 x to the 5th. Then the next term will probably be 3/7 x to the 7th. Okay? When I take x cubed minus 3x plus 3 arctangent of x, well, those first two terms cancel. So we'll get 3/5 x to the 5th minus 3/7 x to the 7th plus higher order terms. And then dividing this by x to the 5th gives 3/5 minus 3/7 x squared plus higher order terms. So the limit as x goes to 0 of our expression of this, x cubed minus 3x plus 3 arctangent of x divided by x to the 5th will be 3/5. Okay? So here we use the power series expansion to plug it into a complicated algebraic expression and simplify so that the limit was easier to compute. Okay, so that's hopefully these few computations that we did are convincing that Taylor series are useful, and that knowing these Maclaurin series is a useful shortcut to computing those Taylor series. Here's one more use. Okay, so we can use familiar Maclaurin series to compute the following sum. We'll start with minus 1 to the n divided by n times 2 to the n plus 1, where n goes from 1 to infinity. Okay, so we want an explicit formula for this sum. Okay? So just looking at it, we wouldn't know exactly what to do with this unless we knew that this looks a lot like the Maclaurin series for ln of 1 plus x, right? So the Maclaurin series, and how could we figure that? Well, we've got an n in the denominator, so that's a good sign that this has something to do with log. So we'll recall that log of 1 plus x is equal to the sum of minus 1 to the n minus 1 x to the n over n, where n goes from 1 to infinity. So, looking at our expression, this is very close to log. We'll want to factor out a 1/2. So let's take this as n equals 1 to infinity minus 1 to the n divided by n times 2 to the n plus 1. Well, this is equal to 1/2 times sum from n equals 1 to infinity of minus 1/2 to the n divided by n. Okay. So that's pretty close to our expression for log, but we want to have this minus 1 to the n minus 1 separate. So actually, let's make this minus 1/2 sum from n equals 1 to infinity of minus 1 to the n minus 1. Okay, and I pulled out an additional minus here so that the sign stays consistent, times 1/2 to the n divided by n. Okay? So, again, that was minus 1/2 times the sum from n equals 1 to infinity of minus 1 to the n minus 1 times 1/2 to the n over n. And this expression is just log of 1/2. So we'll get log of 1/2. You could also, if you wanted, you could recall that log of 1 over something is equal to minus log of that thing. So this is the same as 1/2 ln of 2. Okay. Just one note of caution. You want to make sure that x is in the interval of convergence. Okay. For instance, in this example, x equals 1/2 is less than 1. Okay, so absolute value of x is less than 1, which means that it's in the interval of convergence, so that's why we're allowed to replace it with the function. If it's not in the interval of convergence, then the series is probably going to diverge, and you can't replace it with anything. Okay. Okay, well, we've learned how to compute Taylor series and Maclaurin series, and we've had some practice with different ways to apply this, whether it's computing integrals or limits or evaluating summations. Thanks.